So let's go ahead and do a round of linear velocity. So in this first one, it's asking us to find the linear speed of a point on the edge of a tire that has a radius of 34 inches long and it's rotating at 5 revolutions per second. So I'm going to take advantage of what we've already found, right? Because if we're rotating 5 revolutions per second, well, heck, I'll just go back to the work. That means our omega, right, is basically my time that I traveled, right, excuse me, my theta times the number of revolutions. So that would be 10 pi. And of course we're doing this every 1 second, so as we saw earlier, right, we're getting 10 pi rad. So that's what that basically means. So right now we have our omega, and then they also gave us the radius is 34. So that's tailor-made for our formula, right? So our linear velocity is the radius times my angular velocity. So in this case, v is 34 times 10 pi. And it looks like we get 340 pi, and this would be in inches per second. All right, because this is in rad per second. And remember, rad is technically unitless. So the inches coming from the radius and the per second coming from the rotation, so inches per second. So there's our velocity. So again, that's pretty fast. In the next example, we're at the end of a second hand of a clock, and it's rotating, or excuse me, the second hand is 30 millimeters long. So again, we've already done some work, right? We found that my theta, right, is going to be 2 pi. The time, since it's a second hand, is 60 seconds. So my omega is 2 pi over 60, which is pi over 30 rads per second. So there's my omega, just kind of redoing some work that we did up there. We're told that the second hand is 30 millimeters long. So there's your radius. So again, like this problem here, we have everything tailor-made to get the job done, right? And so basically my velocity, linear velocity, is my radius times omega. And so in this case, my radius is 30. My omega is pi over 30. And so doing a quick cancellation, we get that our linear velocity is pi, and this would be in millimeters per second. Again, radians is technically unitless. Our length, our distance is millimeters, and our time is per second. So millimeters per second. So about 3.14 millimeters per second is how fast something on the edge, again, if we're on a clock and on a second hand, if I was on this edge, I'd be traveling at about 3.14 millimeters per second, according to that example, right, if we had a watch that. Of course, if I increase the radius, I increase the linear speed. Alrighty. Last but not least, we're at a point on the edge of a disk of 2 feet, making a half turn in 0.12 seconds. Well, again, we've done all the work in terms of that. So I'm just going to go ahead and use that. So our omega, as we found, is 50 pi over 6, right, from some previous work. And so all I've got to do is take my radius, which is 2, and then use it in our fancy formula. So v is r times omega. And so in this case, right, our radius is 2, our omega is 50 pi over 6. Of course, if we do a quick cancellation, we get 50 pi over 3. And this would be in feet per second, because our measurement is in feet, and we're in seconds. This is in rads per second, but technically rads is a unitless topic, right, because of the division that goes on. So there you have it. So again, I kind of made use of some angular velocities we found at the top, found some linear velocities on the edge of a circle, and that kind of goes in line with what should be happening, because as we spin around, right, have some angular velocity, as we spin around, we're creating some distance along the edge, which is our linear velocity. And of course, we're on the edge, but if we were to let go, right, we know we'd go flying off like that. So in this case, on a 34-inch tire, we'd be flying off at 340 pi inches per second, right? If we were on the edge of a second-hand clock, we'd be flying off at 3.14 millimeters per second. And here we'd be going whatever the heck that is, 50 pi over 3 feet per second along the edge if we were on a 2 feet wheel taking a half turn in 0.12 seconds. Alright, so there's another round of some homework problems. Of course there's more to do and more to see, but I'll do those in some videos coming soon. Talk to you later.